Consider a different case of diffusion through a stagnant gas film. The case is like this. Consider a system shown in the figure in which liquid A is evaporating into gas B. We imagine there is some device that maintains the diameter of liquid droplet A constant. It is observed for such a case overall resistance to mass transfer is in thin layer around the droplet. Here the layer with inner radius R1 and outer radius R2, I will draw in the diagram and will show you. A stream of gas mixture AB of concentration XA2 flows slowly past the resistive gas film thickness. To maintain the mole fraction of A at XA2 for R is equal to R2, the entire system is kept at constant temperature and pressure. Gases A and B are assumed to be ideal. If mixture of that A and B form an ideal gas mixture and that the solubility of gas in liquid is negligible, derive the expression for concentration profile. So we will first see the figure. Okay. The figure is like this. We are considering a liquid droplet. The diameter of the liquid droplet is R1 and a gas film is surrounding that liquid droplet. The diameter of that gas film is R2. So this is basically the gas film. And the temperature of both the liquid droplet and the gas film is maintained at TR1. So basically this is the case of diffusion through a hypothetical spherical stagnant gas film which is surrounding the droplet of liquid A. Okay. Since in the question it is mentioned that the diameter of the liquid droplet A is constant. So this is radius. So it is given that the diameter of the liquid droplet is constant. So the area, the rate of the flow of the moles, it will be constant. That NAR, which is the molar flux of the liquid droplet, is given as we have previously seen CdAB upon 1 minus XA into dXA by dr. Now since dr r square NAR, which is CdAB upon 1 minus XA dXA upon dr is constant. Again we can move the CdAB here and applying boundary condition 1 and 2 at R is equal to R1, which is at the boundary of the liquid droplet, X is equal to XA1, and at R is equal to R2, XA is equal to XA2. So by applying the boundary conditions, we can get d by dr r square dxa upon 1 minus xa by dr is equal to 0. Integrating it again, we can get C1 r square dxa on 1 minus xa dr. Okay. Now integrating it again. On integrating it, we get this, a constant of integration as we integrate 0. So it will be like C1r dr dxa upon 1 minus xa is equal to C1. Now moving this term on the right hand side, we will get dxa upon 1 minus xa C1 dr upon r square. Integrating both sides, we will get ln 1 minus xa minus C1 upon r minus sign plus C2. Now substitute the boundary conditions, that is at r is equal to r1, x is equal to x1. If we put C1 upon r1 C2 is equal to minus ln 1 minus xa1, and the second boundary condition at r is equal to r2, xa is equal to x2, ln 1 minus xa2 is equal to minus c1 r2 plus c2. So solving both the things and getting the value of c1 and c2 and substituting it in this equation, the final equation that we will get is 1 minus xa upon 1 minus xa1 is equal to 1 minus xa2 upon 1 minus x a1 whole power 1 upon r1 minus 1 upon r under 1 upon r1 minus 1 upon r2. Pause. So this is the equation we get for diffusion of liquid through a stagnant gas film surrounding the droplet. This was our figure. This was our stagnant gas film. Now moving on to the third case. Here the figure is same. The only difference is a temperature gradient has been shown in this figure. Unlike the past question where both the liquid droplet and the gas film were at temperature T1, the droplet is maintained at T1 while the stagnant gas film is at temperature T2, and we have also given the relation of T2 and T1. So T2 is equal to T1 into R2 upon R1 raised to n. So R2 basically is your radius of the gas film and R1 is the radius of the droplets. So the relation has been given. So since the temperature gradient is there, so diffusivity will also vary. DAB and DAB1, we know diffusivity is directly proportional to temperature. So T upon T1 raised to 3 by 2. Again the same condition that d upon dr r square by Na is constant because the diameter of the liquid droplet is not changing, and NaR is given by CdAb upon 1 minus Xa dxa upon dr. Substituting it again, we get d upon dAb1. So as we know, the relation of diffusivity and temperature is this. So dAb upon dAb1 is equal to T upon T1 raised to 3 by 2. And the C, which is concentration, which is given by P by RT. So substituting all this in the R is equal to 0 will become, we know NaR, we know R square. So it will become d by dr r square. NaR is CdAb upon 1 minus Xa dxa upon dr is equal to 0. Now substituting C is equal to P by RT, dAb1 value, it will become like this, d upon dr r square. C is equal to P by RT. In place of dAb1, so sorry, in place of dAb we will substitute in the form of dAb1. So dAb would be dAb1 into T upon T1 whole to the power 3 by 2 upon 1 up minus Xa into dxa upon dr is equal to 0. We know T upon T1 is equal to R upon R1. So this will become like d upon dr r square P dAb1 upon RT upon 1 minus Xa. Instead of T upon T1 we substitute R upon R1 whole to the power n by 2 dxa upon dr is equal to 0. Now applying boundary conditions. First boundary condition, at R is equal to R1, Xa is equal to Xa1. Second boundary condition, at R is equal to R2, Xa is equal to Xa2. Now if we substitute these into the equation, we get, so applying these boundary conditions, and we know P by RT, dAb1 and R1 are constant. So taking them on RHS side, the equation will reduce to dxa upon 1 minus Xa is equal to C is equal to 0 into R2n plus by 2 upon dr. Integrating the equation, we will get whole bracket d by dr. Now integrating the equation, we will get c1 is equal to r 2n by 2 dr dxa upon 1 minus xa. Take this term to RHS. That will be dxa upon 1 minus xa is equal to c1 upon r raised to n 2 plus n by 2 dr. Now again integrating it will give, this will give LHS will be ln 1 minus xa whole minus xa and minus 1 upon 1 plus 1 n by 2 into c1 r 1 plus n by 2 plus c2. Now again clubbing and solving, c1 is equal to ln k1, substituting, c2 is equal to ln k2. It can be like removing the negative sign from the equation. C2 term is negative, so we will consider minus C2 as ln K2. Now substituting these two in this along with the boundary conditions, we get the equation 1 minus xa is equal to K1 1 upon 1 plus n by 2 into r raised to 1 plus n by 2 into K2. This is the final equation that we get after substituting the boundary conditions. Now we can again substitute the boundary conditions here. K1 1 upon 1 plus n by 2 R1 of 1 plus n by 2 minus R2 raised to 1 plus n by 2 this will give us, and solving for K1, this will give us K1 is equal to 1 minus xa1 upon 1 minus xa2 whole to the power 1 plus n by 2 upon 1 upon r1 to the power 1 plus n by 2 minus 1 upon r2 to the power 1 plus n by 2. Similarly, K2 can be written as 1 minus xa1 into 1 minus xa1 1 minus xa2 to the power minus 1 by r1 to the power 1 plus n by 2 upon 1 by r1 to the power 1 plus n by 2 minus 1 by r2 to the power 1 plus n by 2. Here we get K1 and K2 value. If we will substitute this in, so here we have got the K1 and K2 values, as you can see. These are the K1 and K2 values. If we substitute these K1 and K2 values in this equation, let us give it as equation 1. We will get a generalized term, generalized equation. That equation will be 1 minus xa upon 1 minus xa1 is equal to 1 minus xa2 upon 1 minus xa1 to the power 1 upon r1 raised to 1 by n2 minus 1 by r raised to 1 plus n by 2 upon 1 by r1 to the power 1 plus n by 2 minus 1 by r2 to the power 1 plus n by 2. This is the equation that we get. Now substituting that in NAZ, which is PDAB1 upon RT1 raised to n r raised to n by 2 upon r1 raised to n by 2 dxa upon dr upon 1 minus xa. This is the NAZ, which is the molar flux in z direction equation. If we substitute this equation in this and get r value, the equation will be like r2n plus n by 2 upon 1 minus xa dxa upon dr is equal to c1, which is minus ln k1, which is equal to 1 plus n by 2 upon 1 by r1 whole to the power 1 plus n by 2 minus 1 by r2 to the power 1 plus n by 2 into ln 1 minus xa2 upon 1 minus xa1. Simplifying it, we will get, and substituting it in nz, we will get final naz value equation as PDAB1 upon RT into 1 plus n by 2 whole upon r square into 1 upon r1 raised to 1 plus n by 2 minus 1 upon r2 raised to 1 plus n by 2 into r1 raised to n by 2 ln 1 minus xa2 upon 1 minus xa1. This is the final equation of NAZ. Now rate of mass transfer from the surface of the bubble, if we want to find, we will have to multiply the flux into area. Now area would be 4 pi r1 square, since r1 is the radius of the liquid droplet. So the rate of mass transfer from surface of bubble would be area into NAZ, 4 pi r1 square into NAZ, which will give us the final equation as, so rate of mass transfer through the bubble surface would be 4 pi PDAB1 upon RT1 into 1 plus n by 2 whole upon 1 upon r1 raised to 1 plus n by 2 minus 1 upon r2 raised to 1 plus n by 2 into r1 raised to n by 2 into ln 1 minus xa2 upon 1 minus xa1. This is the final equation for mass transfer through bubble.
So our discussion for shell balance for mass transfer actually cleared a lot of my doubts. I used to think diffusion was just molecules randomly bouncing here and there, but now I see how structured it is, especially when you fix one component.
Same here. Once you lock one component, the whole system becomes coupled. Like in the stagnant B case, even though B isn't diffusing, it still moves because A is diffusing. That was counterintuitive at first.
Yeah, the key point was that B is stagnant in the bulk sense, but because A diffuses, it forces B to move slightly in the opposite direction to maintain a steady state bulk flow. That's why we apply the condition JA plus JB is equals to 0.
Exactly. And then using Fick's law, which is JA is equal to minus dCA by dZ.
Right. The derived equation becomes JA is equals to C into DAB upon Z2 minus Z1 into ln of 1 by XA2 upon 1 by XA1.
Oh, and remember how we derived it using shell balance method? We took a differential slice of thickness, did a molar balance over it, and assumed steady state with no accumulation. That step-by-step derivation was a good application of the core balance laws we learned early, right?
Absolutely. It really shows how transfer phenomena is built on just a few principles: momentum, mass, and energy conservation, and everything else is derived, like Verma sir always says in the class. Like we started with balances and arrived at Fick's law under special conditions.
Yeah, and the stagnant gas film model isn't just theoretical. It's actually used in many real processes, like gas absorption, where a soluble gas diffuses through a liquid film, or even oxygen transfer in lungs, where alveolar membrane acts as a stagnant phase.
Good point. And when it comes to ternary systems with three components, it becomes even more complex. The condition becomes JA plus JB plus JC is equals to 0.
Yeah, and that's when the Maxwell-Stephen equations start to show up in a more advanced models, especially when you can't assume ideal behavior or constant pressure. But even in our simplified stagnant film case, the idea is same. Molecular interactions determine flow.
You know what I appreciate the most? The fact that momentum and mass transfer has similar mathematical structure. Like how Newton's law of viscosity for momentum looks just like Fick's law. It reinforces the idea that transport phenomena isn't three separate subjects, it's just one big concept consisting of mass, momentum, and energy balance.
Exactly, it's like a unified language. And the way we use shell balances in all the three cases, momentum, heat, and mass, is just so elegant. You just change the driving force and flux definition.
And academically, this topic really helps build the problem solving framework we need. As engineers, it teaches us how to start with assumptions, apply boundary conditions, integrate, and interpret. No shortcuts.
Yeah, and beyond exams, this is what we'll use in process modeling, reactor design, and separation systems. And anywhere mass transfer happens, like packed columns, gas scrubbers, and even drug delivery systems. This understanding is essential.
Also, I liked how Verma sir emphasized that stagnant films often represent resistance in real system, like a limiting layer that controls how fast something can transfer. Ignoring it can lead to massive design errors.
Exactly, and that's why we are learning this now. Even theoretically, gives us the confidence to tackle real world mass transfer problems later. We know that we know what assumptions are valid and when to dig deeper.
I guess that's the essence of transport phenomena. It's not just what happens, but why it happens and how to control it.
Well said. Now let's make sure we can reproduce that derivation in exam also.
Deal.